So welcome back, and we are going to look at another problem here. This says there's a rigid vessel which is divided into two compartments A and B by a freely floating piston. So let me draw that. So I have a rigid vessel. There's a freely floating piston. Let's assume that nothing can go around the sides of the piston, but so maybe I should draw it closer to this. There's a container A and B. The outside is rigid, it cannot move. Compartment A contains 2 kg of air. A has air, the mass is 2 kg. Pressure is 1 bar. And 25 degrees centigrade. B contains 1 kg of steam water mixture. And quality is 50%, which is 0.5. So what it says is that heat is added to the steam water mixture until saturation. So we are giving heat into this B over here. There is no heat transfer between A and B. Okay, so this piston is frictionless and it's also adiabatic. We are asked to find out the final states of the air and the steam and the heat transfer. Okay, we are asked to find out final states on both sides. So state 2. We are told that we can assume the air in A to undergo adiabatic compression. So A is insulated. So let's insulate the sides because piston can move. So heat is only coming in to this end. So this is what we are asked to do. So A undergoes adiabatic compression. A contains air. Air is an ideal gas. So this is the information we have. We also have the information that the full chamber is rigid. So which means I can have some initial volume here. I can have some initial volume here. And what we know is at any point of time, VA plus VB is equal to VA1 plus VB1, which is a constant. So that is another thing we know. What we are also told is that the air in A undergoes adiabatic compression. So it's an ideal gas. So we can find out the value of gamma. It's air, it's diatomic, gamma would be 1.4. What we also know is for the ideal gas which is in A, so PV to the power gamma would be constant. That is also known for A. So which means we can find out the volume for B from this total minus the volume of A. So all of this is information which we have. The final state for B is saturated. We are adding heat, so it must be saturated steam. So final dryness fraction or quality would be 1 for B. So let's see what we can find out for this. We want initial volumes. So we are going to take air as an ideal gas. We can find out the value of R for the ideal gas. I'm going to do that here. So R is 8314.5 divided by molecular weight. Question of course is what is the molecular weight of air? So if we take air as being like say 79% volume of nitrogen and 21% by volume of oxygen, then we can find out what is the molecular weight. So the volume fractions are also equal to mole fractions. So this is the mole fraction of nitrogen, this is the mole fraction of oxygen. So which means that the mixture molecular weight we had earlier said that it is the sum of the mole fractions into the individual molecular weights. So that's 0.79 into the molecular weight of nitrogen is 28 plus 0.21 into the molecular weight of oxygen is 32. So if we do this, so we get 0.79 into 28 plus 0.21 into 32, which gives us a molecular weight of 28.84. So which gives us a gas constant R of R bar divided by this, which is about 288. So we often take the value of R as either 287 or 288 depending on how many digits and what exactly the composition is. So in reality we know there is nitrogen, there is oxygen, there is also small amounts of carbon dioxide and water vapor and carbon monoxide and a lot of other argon and other gases, but we can approximate it as being like this. So if you did this on a weight basis, we typically consider the composition to be about 77% of nitrogen by weight or by mass fraction and about 23% of oxygen by weight. So that's also something we can do. So we have the value of R here. This is in joule per kg Kelvin. So let's take it as 288. So we can get from the ideal gas equation of state, which says PV is equal to mRT. So V is mRT divided by P. M is 2 kg. R is 288, which we just found. T is 298 and P is 1 bar. So I'm going to substitute those. So I have 2 kg into 288 joule per kg Kelvin into 298 Kelvin divided by 10 power 5. So I get 1.71 meter cube as the initial volume of air. The volume of B I need to find out from steam tables. So B contains a mixture of water and steam. So let me do that over here. So this was for air. Let me look at initial properties of steam. So I can find out Vf and Vg from the tables, and then I know the specific volume is essentially Vf plus x into Vg minus Vf, which I can find, and then V is essentially the small v into m. I'm going to find all of these. So my conditions are 1 kg of steam water mixture at 1 bar. So pressure is given here as 1 bar and quality of 0.5. So since it has a quality which is between 0 and 1, it is a saturated mixture. So what I need to do is look at 1 bar saturated conditions of steam, the pressure table for 1 bar saturated. So 1 bar is 0.1 megapascal. So this is my condition. So the volume is 0.001043 for liquid and 1.694 for vapor. So this is both are in meter cube per kg. The dryness fraction is given as 0.5. So I can find out this now. So this is 0.5. These two are known. So let me find out this value. So I have this as being 0.8475 and I have the mass initially or as being 1 kg. So essentially I have this as 0.8475 meter cube, which I am going to put over here. Since the total volume has to be fixed, the initial volumes were these, so I can sum this up. So the total volume always has to be 2.563 meter cube. So that is something which I know. So we can see what are the information we have. So initial states are fixed, we know all of this stuff. For the final state, what we know is that A undergoes an adiabatic process. So if I take only this control mass, it undergoes an adiabatic process. This undergoes a process where there is heating, and at the end of this process, I know it is saturated steam. I also know that it is a frictionless piston, which means that at any point of time, PA would be equal to PB. So that is also something which I know. So there is not enough information in this to arrive at a solution directly. What I am going to do is to do this iteratively. So what I can do, for example, I can do this either starting from air or starting from steam. So let me start from maybe steam. So I know that finally this is saturated. The initial pressure was 1 bar. I know that the final pressure is going to be higher than 1 bar because I am heating. So let me assume some value of pressure. So what I am going to do, for example, is assume final pressure. So it is 1 bar initially. Let me say, for example, take 2 bar. I don't know what the answer is, so I am going to try to see what it happens. So if I take the value as 2 bar, then what I know is my V2 for B would be the mass into Vg at 2 bar, because at the end of it, it's all supposed to be saturated steam, dry saturated steam. So this would be the volume. So then I know that V2A would be this value minus whatever we calculate over here. And this value which I get, if I put into this, okay, I am calling it V2A, and if it satisfies this initial condition, then it means I have the right answer. If it doesn't, it means I have to pick some other value and then try again. So this is essentially what I am going to do. So let me find out this value. So PA into VA1 bar gamma. So VA1 is 1.716. Gamma is 1.4 into PA1 is 1 bar. So if I take this as bar and this in meter cube, then this value is 2.129. So this is bar into, or let me just multiply by 10 power 5. Okay. This is in Pascal into meter cube to the power of 1.4. So that's essentially what I get. So let me see what this happens. I am assuming P to be, for example, 2 bar. So what I need is specific volume of the vapor. So I need from this at 2 bar, which is say this value, I need Vg, which is 0.8857. Mass is 1, so that is, this is in meter cube. So now I am going to have V2 of A which is 1.6773 meter cube. So now using this value of V2A, I am going to calculate this. So I have this to the power of 1.4. So P2A into V2A to the power gamma is this power 1.4 into pressure is 2 bar. So I get this value as 4.12 in 10 power 5. It should be 2.1 in 10 power 5. So clearly my guess is not very good. So assuming P2 as 2 bar did not give me a very good answer. So let me try again. I am going to take a value lower than this. So let me now assume, for example, P2 is some, let me see what I have values of in the steam tables. Okay, I have 0.14, 0.16. Let me take 0.14 as somewhere in lower. I know it is greater than 1. So let me take 0.14. So then V2 for B is M of B, which is 1 kg, into Vg at 1.4 bar or 0.14 megapascal. So let me see what that value is. So if I take 0.14, Vg is 1.237. This is the value which I get. Now V2A must be the total sum we had, which is 2.563 minus this value. What I am once again going to see is whether I can PV to the power gamma is how much. So that's 1.4 in 10 power 5 Pascal, or 0.14 into 10 power 6 Pascal, into 1.326 to the power of 1.4. Which gives me 2.07 into 10 to the power 5. This was supposed to be 2.12 into 10 to the power 5, not very far away from what I have got. So if I had tables with finer digits, I can find out this to closer, but this is not bad. So I am pretty happy with my guess of 0.14. What I can do is see if I can get a better answer with, for example, 0.16. If I was to take 0.16, I would have this as 0.001054. So let me do that and see. This is Vf, which is not really useful to me. I need Vg. Vg at 0.16 is 1.091. So Vb2 would then be 1 kg into 1.091 meter cube. Va2 or V2A, as we are calling it, both are the same, would be 2.563, which is the total volume minus this volume. Which is 1.472 meter cube. And I can find out P2A is P2 anyway. This is pressure into volume to the power of gamma. So I get this value as 2.74 in 10 to the power 5. Whereas I need a value close to 2.1 in 10 power 5. So, of all the calculations I have, this is 4 in 10 power 5, which is very far away. This is 2.7 in 10 power 5 and this is 2.07 in 10 power 5. I need 2.1 in 10 power 5. So, this seems to be the best estimate I have. So, this is one of those problems where we see we need to do a little bit of iteration to get the final answer. So, not all problems have equations where you can directly solve them. So, these kind of problems you would have to iterate and find out the final answer. So, here this is a pretty good estimate. So, what I wanted finally is to find out the final states. So, the state in this case, the pressure in both cases is 0.14 megapascal. The volume for A is 1.326 meter cube. For steam, pressure is again 0.14 megapascal. The volume of the steam is 1.237 meter cube. In the case of steam, I can also tell the temperature directly, because at 0.14 the temperature is 109 degrees centigrade. In the case of the gas, I do not know directly the temperature, but I can use the ideal gas equation of state to find out the temperature. So, T, I know the pressure, I know the volume, so I know PV is mRT. So, this is PV by M into R. I know R is 288. So, I know the pressure here, I know the volume. So, I have 0.14 in 10 power 6 into the volume of A divided by the mass of the gas, which is 2 kg, divided by R, which is 288, which gives me a temperature of about 322 Kelvin. So, since it is insulated, so I have the gas temperature being different from the steam temperature. So, this gives an example of a problem where we have a system containing both gas and steam. So, we deal with the gas using the ideal gas equation of state, we deal with the steam using steam tables, and we can find out interactions between both of them in this case.